There is a subtle dishonesty in a perfectly clean room. You can place a high-precision mechanical joint on an optical table, send it a stream of step commands, and watch it move with total, repeatable grace. In that controlled space, the mathematics feel complete. The equations describing torque, inertia, and magnetic flux line up precisely with what the sensors report. For a moment, you are allowed to believe that physical reality is simply software waiting to be rendered. To teach machines how to move through our world, we realized long ago that physical trial and error was too slow. A physical robot breaks. It overheats. It requires technicians, replacement parts, and time. So we built synthetic worlds. We took classical mechanics, fluid dynamics, and contact models, and translated them into raw computation. Inside these digital spaces, time is an arbitrary setting. A control policy can live 10,000 lifetimes in a single afternoon. It can fall down 1,000,000 times, reach for 1,000,000 targets, and gradually shape its artificial neural network into a masterclass of kinetic efficiency. To bridge the gap between this idealized digital void and our messy world, we developed clever techniques. We learned to randomize the simulated parameters. We varied the friction of the floor, shifted the center of mass by a few millimeters, added synthetic sensor delay, and injected Gaussian noise into the motor commands. We convinced ourselves that if we made the digital training ground chaotic enough, the model would become resilient. We called it domain randomization, and for many tasks it felt like magic. The policy would deploy into a physical robot, adapt instantly to a slightly slippery table, and perform its duty with unnerving perfection. Yet, if you leave that robot running for 3 days or 3 weeks, something subtle begins to change. The control policy has not altered its weights. The sensor pipelines remain intact. The input data stream looks virtually indistinguishable from the synthetic training distributions. But the physical motion begins to stutter. A micro-oscillation appears at the end of a reach. A joint hesitates for 3 milliseconds before overcoming static friction. A trajectory that once looked fluid starts to carry a barely perceptible tremor. We tend to diagnose these failures as unexpected edge cases or physical defects. But the truth is more fundamental, and perhaps a bit more unsettling. The failure was not caused by a flaw in the code. It was caused by a quiet assumption built into the very foundation of synthetic physics. In a physics engine, parameters are represented as variables within an environment. Friction is a scalar value. Backlash is a geometric offset. Viscosity is a constant in a differential equation. When we perform synthetic training, we assume that these variables, even if randomized, are static properties of the environment. We treat the world as a stage that remains stable while the actor learns to perform upon it. But a physical mechanical actuator is not a static mathematical parameter. It is a dense, violent, heat-generating convergence of matter. It is steel gears grinding against bronze bushings, synthetic grease under continuous shear stress, and copper wire cycling through rapid thermal expansions. When a synthetic model operates in the real world, it encounters something no physics simulator has ever truly captured with fidelity. It encounters where. Where is not noise. Noise is symmetric, memoryless, and bounded. Where is history written directly into the material structure of the world. It is the irreversible accumulation of microscopic damage. It is a tiny ridge polished into a bearing raceway after 1,000,000 rotations. It is the subtle migration of grease away from a high-pressure gear tooth contact point due to high angular velocity. It is the gradual loss of surface hardness on an anodized shaft. In a simulation, every episode reset clears the slate. The digital universe returns to time zero. The simulated actuator is reborn fresh, entirely innocent of its past actions. But real hardware cannot forget. Every single torque command applied to a physical motor burns a fraction of its operational life. Every rapid direction change leaves an indelible signature on the tooth profiles of its reduction drive. The physical robot is not merely moving through space to achieve a goal. It is consuming itself to execute the command. When an artificial intelligence trained entirely in synthetic physics experiences Actuator where its internal model of reality begins to drift away from the physical truth. but it does not drift in a way the model understands. When the agent senses a delay in motion, it does not realize that a microscopic flake of hardened steel has broken free and lodged itself in the lubricant of the planetary gear set. The agent only knows that the measured state does not match the expected state predicted by its billions of simulated trials. Operating on the core assumption that the physical world obeys the laws of its digital cradle, the neural network adjusts its output. It commands more current to force the joint into compliance. The extra current drives up the internal temperature of the motor coils. The rising heat lowers the electrical resistance, alters the magnetic permeability of the stator, and thins the remaining lubricant inside the gearbox. The wear accelerates rapidly. The policy, acting with absolute mathematical confidence derived from an infinite synthetic upbringing, aggressively drives the physical system directly toward catastrophic degradation. It is trying to solve a permanent, structural shift in reality using solutions designed for temporary elastic disturbances. This reveals a deep paradox at the heart of our attempt to digitize physical intelligence. We built synthetic physics on the foundation of equations, and equations are elegant descriptions of idealized balances. They describe conservation laws, energy transfer, and continuous trajectories. But equations do not easily capture entropy. They do not reflect the asymmetrical, deteriorating nature of reality. In our pursuit of scale, we built worlds where action has no long-term material consequence. We created synthetic environments where an engine can run at maximum load forever without ever burning its oil, where a joint can reverse direction 10,000 times a minute without ever galling a surface. We taught our models that motion is free, and that the universe resets when things go wrong. Then, we place those models into delicate structures of alloy and copper, and we express surprise when they fail to comprehend the slow, persistent decay of the physical frame. Standing near a running robotic cell, you can hear this failure long before the diagnostic software flags an error. You can hear it in the acoustic signature of the system. The high-frequency whine of the pulse-width modulation blends with a low, irregular rasping sound coming from deep within the drive housing. It is the sound of an artificial mind trying to enforce a smooth, timeless mathematical truth upon an object that is slowly, relentlessly falling apart. Eventually, the error signal crosses a critical threshold. The control loop panics. The software throws a safety fault, and the arm locks its brakes, coming to a dead stop in middle-air. A human technician will walk over, plug in a terminal, and read the fault log. It will say position error, or current limit exceeded, or tracking limit reached. The technician will replace the modular actuator, recalibrate the 0 point, clear the fault, and press start. The control policy will instantly recover its flawless grace. The motion will become smooth again, crisp, and seemingly immortal. Everything will appear to be back in balance. If an intelligence can only understand a world that never degrades, how much of our reality does it actually comprehend, and what happens when we trust it with systems that cannot be replaced?